Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So what we are going to be doing now is the last big push of the class, Chapter 6, in which we are going to tie some of the threads together that we have been laying down all term and connect them all in order to solve some very interesting and very practical real-world type of problems. But where we will start is in section 6.1, where we will be talking about three main things: the inner product, length, and orthogonality. Alright, so that's the agenda. Alright, we will start by taking a look at our setup. Our setup is going to be, we are going to be looking at vectors in Rn. So we are going to be looking exclusively at vectors here. There's not going to be any mention of any matrices, just vectors. So setup, vectors in Rn. And by vectors in Rn, we just mean nice, good old-fashioned column vectors. Nothing too crazy, nothing too exotic. We're not talking about like polynomials or anything like that. Just regular old vectors in Rn. Okay, first off, the inner product. So the inner product, that's sort of the most technical name for it. The slightly less technical name for it, although still pretty technical, is the scalar product. But there's one name that's even more informal and even more common, and that would be the dot product. So it's written, typically written with a dot, and so as opposed to the other kind of product of two vectors, which is the vector product, which is written with a cross, this one is typically referred to by the nickname dot product, which is a shout out to its notation. So the inner product. So given U and V both in Rn, U dot V, that'd be the usual way you'd pronounce that, U dot V is equal to, now here's one way of putting it. You could say, think of this column vector as really being a little matrix of one column, and it would be the transpose of that matrix times the matrix V, where this is just regular matrix multiplication. It would also, this could be written in another way. We could just express it as component by component multiplication, and then the sum over all of those. So it would be ui, vi, the sum of those as I goes from 1 to n. So what we're talking about here would be the ith component of u times the ith component of v, the sum of that over the n. Now this way it looks less, it looks a lot less comprehensible, but it actually is a lot more practical when it comes to actually calculation if you unpack what this actually means. So for example, if u was equal to, let's say, a, b, c, d, and v was equal to e, f, g, h, then u dot v would just be that times that, plus that times that, plus that times that, plus that times that. So this is the way we'll actually typically evaluate these things, these dot products, also known as scalar products, but more formally known as inner products. Okay. Now, as an example of doing something like this, let's just try something. So, example, let's just say that u is equal to 1, 2, 3. And let's say that v is equal to 4, -5, and 6. Okay, there we have two vectors, u and v. So let's compute the following. Let's just say first u dot v. Okay, so u dot v. And always write the dot. The dot is not optional here. So when you're multiplying numbers or algebraic expressions, sometimes you can put in a dot, sometimes you can leave it out. Here, this dot is not optional. It is an important piece of notation because there are there's more than one way to do vector multiplications, and this is one of them, written with a dot. So this would be 1 times 4 plus 2 times -5 plus 3 times 6, which would just be 4 minus 10 plus 18, so I believe it's going to add up to a total of 12. Alright, so u dot v looks like that. B. So that's the kind of simple thing we could do, but we might do something more complicated, and this is the kind of thing that actually comes up pretty frequently in certain kinds of calculations. We'll see in the next section what this actually is accomplishing, but u dot v divided by v dot v, and that all times u. No, that's a dot, that's a dot, that one is not a dot. So this is a kind of calculation that comes up with some regularity, and here we can evaluate this and see what we get. And basically, just do it piece by piece, the same way you would evaluate any other complicated piece of mathematical notation. You just go. So I'm just rewriting it here. I'm also strategizing. So I'm just going to do the first dot product on the top, the second dot product on the bottom, and that's all going to be times u. So then what we've got here is in the top, well, we already actually did this calculation. It's 1 times 4 plus 2 times -5 plus 3 times 6 downstairs. What we have is 4 times 4 plus -5 times -5 plus 6 times 6, and that's all times u, which I'll just continue writing as a u. And now what this is going to be giving us is, of course, 12, as we already evaluated up there. Down here we're going to have 16 plus 25 plus 36. So 16 plus 25 is going to be 41 plus 36. It's going to be 77. Alright, and then just as a final note, this u was actually a vector, and so if I wanted to evaluate this all out, that would be 12 77ths times 1, 2, 3, which would in turn, if I distributed it in, be 12 over 77, 24 over 77, and 36. over 77. Now, what does this actually represent? Well, that's a matter, again, as I said, for another section. The next section will discuss what such a calculation would actually mean, but this is, in the meantime, how you would actually do it. Alright, so now some properties of the inner product. So this is called by your book a theorem, but really it's just a statement of some properties. Properties of inner products. Okay, so set up here. Just gonna have U and V are any elements of Rn. Alright, and C is any scalar. Alright, and here come our properties. So first off, the inner product is commutative. U dot V is the same as V dot U. Alright, so it's commutative. This, by the way, is not the case for the vector product, for the cross product. The cross product is not commutative. It is anti-commutative, actually. So if you interchange the order of two vectors in the dot product, no difference. If you interchange the order of two vectors in the cross product, the result becomes the opposite. Oops, I meant here, by the way, for there to be a third vector, W. So U, V, and W are any elements of Rn, because I also want to explore the distributive property. You need three vectors to do that. So U plus V dot W. This is the same as, and it's just what you would hope it would be, U dot W plus V dot W. And because of the commutativity, this actually works the other way as well. So if I had U dot V plus W, this would be the same as U dot W plus U plus V, I should say. Start over. U dot V plus U dot W. Alright, so it is distributive in all the regular ways. Distributivity, by the way, is what makes a multiplication a multiplication. If it doesn't have a distributive property, then it's not really the kind of thing that we would typically write with some sort of notation that implies multiplication. Alright, and then let's see, if we have C U dot V, that's the same as C times U dot V, and that in turn is the same as U dot CV. So what this means is a scalar multiple will always end up with the same result, whether you multiply it on just one of the vectors, just the other of the vectors, or just the product. Alright, so these are all pretty basic properties. Now here is one that's more interesting. So u, this is what's called the positive definiteness of the inner product. U dot u, so u dot itself. So this is always greater than or equal to 0. Dot products always produce numbers, they always produce scalars, and this is a scalar that is always going to be non-negative with u dot u equals 0 if and only if u is the 0 vector. So what this is saying is a dot product is always going to be producing some scalar. If you take a dot product of a vector with itself, that means that will always be a non-negative scalar. And as long as the vector isn't 0, it'll actually even be a positive scalar. Now, because this is a positive scalar, we can take the square root of it. And taking the square root of something along these lines is exactly what you would typically think of as finding a length or a distance. So the definition, the length or also called the norm or the magnitude sometimes even called a modulus, but that's less common. That's more a thing that you use to refer to complex numbers. So the length or norm or magnitude of a vector is given by, so the way we can write it, there are different notations. This is a double absolute value bar. You can also see it sometimes with just a single absolute value bar. There's no standard notation on that. It can go either way. This is what your book uses. So that's what we'll use as well. So this is equal to the square root of v dot v. Now, if you unpack what that would mean, that is in other words the square root of, and we just take it entry by entry, v1. Oops. So this is not a vector. It's v1 times itself, so in other words squared, plus v2 times itself squared, dot dot dot, up to the last one, vn squared. So as an example, let's say that v equals 5, 6, negative 7. Then the magnitude of v, sometimes this is also called the absolute value. The magnitude of v, or the length of v, or the norm of v, is equal to the square root of 5 squared plus 6 squared plus negative 7 squared. And don't forget, these are this is the whole number squared, so the negative will get canceled away. So what we're going to have is 25 plus 36, so that's 50, that's 61, plus 61 plus 49 is equal to 110, so square root of 110. And you can do these things also in a calculator. You don't need to be a hero here. We will usually leave these things in a more or less unevaluated format. We won't even really go too all in on simplifying these as far as pulling out perfect square factors. Although this one doesn't have any perfect square factors anyway, because this would be 10 times 11, and so there's no perfect square we can pull out of such a thing as this. But we'll be a little loosey-goosey in leaving things in these square root formats. Also, we're not going to go nuts on rationalizing denominators in here either. So So that's just a note about where we're going to be fighting our arithmetic battles. It's not going to be so much on the field of simplifying square roots. Now, unit vectors. These represent vectors of unitary magnitude, in other words, magnitude 1. So these are vectors of length 1, and sometimes denoted by a caret or a hat instead of the little arrow on top. Now, we can find a unit vector that goes in the same direction as any given non-zero vector by doing the following. So note, if v is not equal to the zero vector, we can find a unit vector in the same direction as v by doing the following. So we could say v hat is equal to v divided by the magnitude of v. So if you divide a vector by its own magnitude, then the magnitude will become 1. And this, you can also write it as 1 over magnitude of v times v. And we can do this, for example, for the v that we just, we might as well just use that same v again, for the v of 5, 6, negative 7. Find the unit vector with the same direction as v. Alright, so then magnitude of v, as we already calculated, was equal to the square root of 110. And then that means that the unit vector that goes in the same direction as v, v divided by that, which will be 1 over root 110 times 5, 6, negative 7, which we will evaluate this far and no further. We'll distribute it in, but we will not rationalize the denominator. We will not go crazy here. We're not going to rationalize the denominator. We're not going to evaluate it as decimal. We're just going to leave it in this format. The most we will do is we will distribute it in to the entries. Now another application of the inner product, which also is an application of the formula for length, is to find the distance between two vectors. And really this is a little bit misleading. It's the way your book words it. It says distance between two vectors, but really what it means is the distance between 2 points represented by position vectors. So distance, but we'll just copy the wording of the book. Between vectors u and v is given by, and then the way we write it is dist u comma v, and it's the magnitude of, or the length of, or the absolute value of, all ways of wording this, u minus v, like so. Now, be careful, you can't distribute this into this subtraction the way you also couldn't do that for regular absolute value. So this is a thing that you have to evaluate entry by entry, and then you have to apply the appropriate formula for this. This is, by the way, also called a metric. So the distance, also called a metric. So this is called the Euclidean metric. But that's not really so important for us right now. Let's just look at an example. So let's take as an example, u is equal to 3, 2, 1. V is equal to -5, 1, 6. Alright, well then, what we want here is the distance between u and v is equal to, well, let's first figure out u minus v. That'll be the easiest way to go about this. So we are going to need to subtract u minus v entry by entry. So that's going to be 3 minus -5 is 8. 2 minus 1 is 1. 1 minus 6 is -5. And then if we think about how you calculate the length of a vector such as this, it would be just the square root of that squared plus that squared plus that squared. So it's going to be 8 squared plus 1 squared plus -5 squared. And that's going to equal, so it's going to be 64 plus 1 is 65 plus 25 makes 90. And again, we are not going to worry too much about pulling out any perfect square factors that we could from here, even though in fact 90, we can clearly see that we could pull out a 9, for example, from that, and then that would give us 3 root 10, but we're not going to break our backs in simplification of these particular kinds of square roots. All right. Now, here is the last major topic of this section, orthogonality. So there's a lot to say about this, and it's a long word. Ortho means right. That's so, for example, orthodox in religion means having the right beliefs. Or it can also mean like straight. So like orthodontist is somebody who straightens out your teeth. Orthopedic straightens out your feet, things like that. So ortho means straight or right. Gon means angle, like polygon. So this means right angledness. So this means perpendicularity. So two vectors are orthogonal, meaning they are perpendicular if this is the case. So U and V are orthogonal if and only if U dot V equals 0. Now, this leads us to, so now that we're actually, I guess as an example, let's say we have U is equal to 3, 1, negative 2, and let's say that V is equal to 1, 3, and then 4. So are U and V orthogonal? Well, you just crunch the numbers and see for yourself. So what do we have? We have U dot V is equal to 3 times 1 plus 1 times 3, and then plus negative 2 times 4. So it's going to be 3 plus 3 minus 8 is negative 2, which is not equal to 0, so no. Alright. What if, in contrast, we had U is equal to 3, 1, negative 2, and V is equal to 1, 3, and 3. Are these U and V orthogonal? Well, let's find out. U dot V is equal to 3 times 1 plus 1 times 3 plus negative 2 times 3, which is equal to 6 minus 6 equals 0, and the answer is yes. Alright, so that's how you determine if two vectors are orthogonal or not. Now, let's take a look at what the vector version of the most celebrated geometrical fact ever discovered by humanity was, or would look like. So, let's take the old classic Pythagorean theorem. So we all know and love the Pythagorean theorem in its classic geometric formulation, which has to do with the sides of a right triangle, and in particular the square of the hypotenuse is equal to the square of leg 1 plus the square of leg 2, usually a phrase, a squared plus b squared equals c squared. Well, here's what the vector version of this would be. So U and V are orthogonal if and only if and only if the magnitude of U plus V squared is equal to the magnitude of U squared plus the magnitude of v squared. So what this is saying is we have got ourselves, in fact, a right triangle if the square of the length of, let's say, u going that way, and v, let's say, going that way, is equal to the square of the length of the sum u plus v, which goes like so. So this side squared equals that side squared, that side squared. That's a fact that's true for right triangles. That's the usual direction of the Pythagorean theorem, but it's only true for right triangles. That's the other direction. That's usually called the converse of the Pythagorean theorem. So the Pythagorean theorem here would give us this equation, if and only if. Now, if we are not so interested in it being a right triangle exactly, then we can actually expand this a little bit. So if you think about what you know from the rules of trigonometry, the Pythagorean theorem only applies for right triangles. But if you have something that is not a right triangle, then the next best thing is the law of cosines. So the law of cosines, in the case of vectors, actually has a little bit of an interesting little flair to it. So the law of cosines here, let's take the situation and rearrange it ever so slightly. So let's say what we have is a u that goes like this, a v that goes like this, and then we want to make a triangle out of it. Let's say this is the angle of theta between u and v. And so if we want it here, we can go this way, and this would be u minus v would be the triangle that goes from v to u, or like so. But that's not really so important, because we're going to be taking magnitudes of all of these. So if I want the magnitude of u minus v, this is going to be equal to, u minus v dot u minus v. So it'd be like the square root of this squared. So in other words, those cancel each other. And then if we distribute this all in, and distributing this is actually just like FOILing, thanks to the distributive property, which is one of the properties of scalar multiplication. It's going to be u dot u minus 2 times u dot v plus v dot v. But this is equal to the magnitude of u squared. This is equal to the magnitude of v squared. And this is equal to that part. So this is the vector version of the law of cosines. Now, what this means is, the consequence of this, if if you think about the regular version of the law of cosines, this is equal to, so this part right here is actually where you would usually see AB cosine C. So what we have as a consequence of this, so if we compare this with standard law of cosines, we see u dot v is equal to magnitude of u, magnitude of v, cosine of the angle between them. And this is how the dot product is often defined, particularly in a physics class, but it actually is just a consequence of the law of cosines. So this, which we're not going to do so much, but one could, this can be used to find angles. Between vectors. But again, that's not going to be our focus in this class. That's the kind of thing that does happen often in all sorts of different situations, from physics or vector calculus. But it's not really our bagatelle right now. So that's just like a little bit of an aside. It's an interesting little connection back with some of the geometry that we all know and love from our trigonometric investigations earlier on in life. But now, let's introduce the last major concept of this section, and that's orthogonal complements. So the setup here is that W is a subspace of Rn. Then W perp, and it's written like this, so you pronounce this W perp, like as in perpendicular, and you write it with an upside down T. So W perp, so like the usual symbol for perpendicular, this is equal to the set of all V that belong to Rn such that V dot W equals 0 for all W in W. So in other words, this is the collection of all vectors perpendicular to every element of W. So the collection of vectors perpendicular to every element of W. But what, you might be asking yourself, does this have to do with bases and dimension and things along those lines for this particular for this particular subspace? Well, I'm glad you asked. So here's a theorem that'll address just that. So here's a setup. Alright, what we're going to have is W is a subspace of Rn with basis B, which equals, let's say, B1 through Bk. So in other words, W has dimension k. It's a k-dimensional subspace of Rn. So then, 1, x belongs to W perp. So x belongs to the orthogonal complement of W if and only if x is orthogonal to each element. So by definition, we know this would be to each element of W, but if we have a basis, then that actually makes this a little bit simpler to check. It's just each element of B. So each of the B elements here. So x is perpendicular to each of these k elements. That implies that x is an element of W perp. So that's that. Number 2, W perp is a subspace of Rn with dimension n minus k. So in other words, what this was saying was the dimension of W was k. So W perp is a subspace with dimension n minus k. And the third and final property that we're going to say in this theorem, the only element of Rn that belongs to both W and W perp is the zero vector. Only the zero vector belongs to both of these subspaces. Because they're both subspaces, they both must have 0. But that is their general obligation as subspaces, but they do not go above and beyond that. All they share is the zero vector. Now, if A is an m by n matrix, we can actually go a little further. So we can spell out more directly certain relationships between the vectors of the null space and the vectors of the row space. In particular, row space of A and the orthogonal complement thereof. So the orthogonal complement of the row space of A is equal to the null space of A. And the orthogonal complement of the column space of A is equal to the null space of A transpose. So here, there's actually kind of an interesting, it's an interesting relationship between the upside down T and the right side up T. And in particular, here we're talking about the transpose of A, the null space of that. That's equal to the column space. That's equal to the perpendicular, the orthogonal complement of the column space of A. So then, if we want a basis for W perp, we can use this with the elements of A or we should say with the elements of B as the columns of A. So as an example of this, let's take the following. So let W be a subspace of R4 with basis, let's say B is equal to 1, 1, 1, 1, and 1, 0, 1, 0. Okay, so there's the subspace, there's the basis. Find a basis for W perp, so the orthogonal complement to W. All right, so let's think about this. We need to find the deal, or we need to find a basis for the orthogonal complement of this. And if we look here, that will be the same as finding the orthogonal complement of the column space of an A made out of these. And to do that, we can use the null space of A transpose to get us there. So if A is equal to 1, 1, 1, 1, 1, 0, 1, 0, then W is equal to the column space of A, which means that W perp is equal to the orthogonal complement of the column space of A, which means that it's equal to the null space of A transpose. So let's figure out what A transpose is. So A transpose, that would be 1, 1, 1, 1 as a row instead of a column, and 1, 0, 1, 0 as a row instead of a column. So now we need to find the null space of A transpose. So what we'll do is we'll take A transpose and we'll augment the 0 column on it, as that is the usual formula, the usual procedure for finding a null space. Because after all, null space is exactly the set of solutions to this very homogeneous augmented system. And then we would just row reduce this and get what we get. So by the look of things, we're going to have a better time if we put that one as the first one. And then if we also subtract it, we can see we're going to get this. Also, you can use technology on these. You've put in your dues. You've done a lot of row reduction by hand over the course of this course, so no harm. Just relaxing, letting senioritis slip in, and using a calculator for something like this if you want. But now let's think about where this leaves us. So this is, of course, x1, x2, x3, and x4. And so x1 and x2 are both basic variables. x3 and x4 are both free variables. So x1 is going to equal negative x3. x2 is going to equal negative x4. x3 is going to equal x3, the free variable. x4 is going to equal x4. And what that's going to lead us to is that the x's that look like, or that would satisfy the system of equations would be negative x3 generically, negative x4, x3, x4, which we will do our usual thing of pull out the x3 and look at its terms. So it's going to be a negative 1, a 0, a 1, a 0, and then plus x4, a 0, a negative 1, a 0, a 1. And so then this is going to serve as our basis. So our basis for the null space, in other words, the orthogonal complement, is going to be these. Negative 1, 0, 1, 0, and 0, negative 1, 0, 1. And if you wanted to check these, you can check, are these perpendicular to the elements of B? So you can do the dot products here, and you can check it by doing, so negative 1 times 1, here, you can see it better right here. So negative 1 times 1, and it's going to make a negative 1 plus 1 equals 0. And here, negative 1 plus 1 equals 0. Here we have negative 1 plus 1 equals 0, and 0, 0, 0, 0 equals 0. So we have our two elements that are each perpendicular to each of the elements of this basis, and so this will be a basis for the orthogonal complement to W. Alright, well that's going to do it for this section. Join me for the next episode of Math 261, which will be section 6.2. Alright, till then, bye!